All right, welcome everyone. Today we're going to kind of finish out our discussion with our multiple integrals, our triple integrals, this time looking at spherical coordinates. In our first introduction to triple integrals, we did rectangular, Cartesian, right, our typical x, y, and z, looking at those typical rectangular prisms, little blocks of volume dV, stacking those up, filling that space, okay? But then when we saw that our region over which we're integrating is more circular, right? But we still kind of maintained like a cylinder, of course, but maintain that kind of Z aspect, or we can reorganize. We use cylindrical coordinates with that kind of polar format layered with the Z axis, okay? So now what we're gonna start to look at is our next possibility of different coordinate systems, this time spherical coordinates. Okay, so let me start to share my screen, the docam, and we'll get going into that discussion. All right, so here we are, triple integrals in spherical coordinates. So we had done before, right? Again, our regular rectangular or Cartesian coordinates, just to reinforce. When we had some region, three-dimensional region that we're integrating throughout. Oh, sorry, my pen here. All right, so we have this space E. We're going to build up these little rectangular blocks of volume dV. Where we can assign dimensions to those, right? dy, dx, trying to organize kind of in that same aspect, dz. And we saw that that dv component we see in our integral, we can label, we can reorganize if we need to, right? For that dv. And so we start to see some function in three variables that we're going to apply throughout that region E, adding up those actions of our function, those little bits of volume, adding up. And we talked about it. We can set up that integral with a dv being dx, dy, dz, and just being mindful, careful of how we set up those limits of integration. Okay. Let me get this up higher. There we go. Okay. And so that was what we had started with. Again, drawing that region, imagining those columns of volume, and then placing those dv, those little blocks, and working our way through was always helpful for myself, figuring out kind of in that xy plane or whatnot, the domain, the shadow, the projection down, what region we're integrating over, kind of like our double integral, and then extending that in the z direction for those limits on z, okay? But again, if we reorient, we can always have our domain space be in the xz plane, yz plane. It just matters how we organize and kind of see how those surfaces are interacting to get those appropriate limits on those integrals, okay? And then what we covered in the next discussion are cylindrical coordinates. But now instead of having our typical x, y axis, right, we kind of still superimpose that. But now what we identify that if our region over which we're integrating looks more like a cylinder, or integrating throughout, I should say, more of a cylinder, right? If that's our region E, then instead of our rectangular box, which of course we can do, but those limits get a little bit more messy. What we start to find is instead we can look at these little kind of portions of volume as these kind of curved pieces, right? And these different locations of those blocks, okay? We're going to need this theta, how far out we are, r, and then the z part, the height still, right? I know it's a little messy there, but looking at that point, we can locate, okay? But the idea is that we have for this dv, again, this little kind of arced component of volume, where the height is still the dz, how far we're sweeping out or out this way direction, the width of it, dr. But now the interesting part, how far we're sweeping out, was that r d theta. It's not just how much angle, but because there's a little arc to it, that arc length r d theta. So then our dv component becomes that r d theta, sorry, dr dz, which we can rearrange in any order. And so when we start to integrate over e, our function of x, y, z, dv, now instead, over that region e, we get a function of r and theta, converting x and y to r's and thetas. Z stays the same. And then for our dv, that r, d theta, dz, I rearrange here and just trying to keep it relatively clean, but we can rearrange those as necessary. So now what we're going to discuss, if our region E is a spherical region, right? So now if we're enclosing some space inside of a sphere precisely, again, the same way that this kind of arc is easier to manage in polar, the r's and thetas, a sphere is going to work more well with these spherical coordinates we'll talk about. Or a cone, similar idea, okay? So whether we have in our space here a sphere through which we're integrating, okay? And again, trying to draw this, but quickly, we get our sphere here. I know it's kind of messy. The textbook has much better diagrams. Or even like a cone through which we're integrating. Because of the fact that we have that kind of circular look to it, using our typical Cartesian XYZ coordinate system might not be as supportive. Even this polar or the cylindrical form, say again, that you got polar for XY and then Z stay the same. That cylindrical form may not benefit this case either, the way that arc, that sharp angle is here, and then we're looping the circular region. It might not be as quick to identify those limits. So instead, we're going to use, okay, can use spherical coordinates. And again, it's a way of rewriting with different variables, different relationships, to hopefully simplify the integral, the expression, the function that we're integrating, and those limits of integration that we need for that space. Okay. All right, so let's introduce those spherical coordinates. Right. And so if we look at our typical Cartesian rectangular coordinate plane or coordinate system in 3 dimensions, not a plane anymore. Okay. We can identify some point out here at X, Y, and Z. So with cylindrical formats, right? Remember, we would kind of imagine projecting this down. And with cylindrical coordinates, we can identify this value theta, how far out that point is going to swing from that positive x-axis, that theta equaling 0. At y, theta pi over 2. And we can measure that distance out. I'll make it a solid line this time, r. And we had that x was equal to r cosine theta, y was equal to r sine theta, x squared plus y squared was r squared. Okay, those relations we talked about how to find theta as well. And then we kept z the same with cylindrical. But now with spherical coordinates instead, we're going to have that measure out in this direction. But now we're also going to measure some information in this regard, right? So from the origin, from our center, we're going to measure, this is our Greek letter rho, right? Like our Greek R, if you will. All right. And then now pay attention to this part, measuring from that positive z-axis out to that radius, that measurement from the origin to our point. We're going to give this the angle phi, okay, or phi, that angle. This angle from that positive vertical z-axis down to that radius from the origin to our point. So this would correspond to phi being equal to 0. We're going to sweep down, so the negative z-axis would be the phi being pi, okay, at the y or the xy plane. Phi would be equal to pi over 2, okay? Negative z-axis, phi is pi, okay? So you can see how far down we're going to arc. So we can start to measure this location, that point, in terms of rho, theta, phi. Okay, and I think that's the typical order that we organize. Our coordinates, rho, that distance, that radial distance from the origin to our point. Theta, how far out we're going to swing from that positive x-axis. And then how far down from the z-axis we need to go. Those are our locations for that same xyz point. Okay. And so looking at that through some geometry work, this is the same as this triangle. I guess I could put this in solid. Here's my right angle. Here's R. Here's rho. This angle also phi, right? Kind of opposite interior angles are going to be equivalent, congruent here. So if we look at that, there's my angle. Notice that we have here that the sine of that angle phi, opposite over hypotenuse, r over rho, or this is equivalent to seeing that r multiply both sides by rho, rho sine phi. Okay, so translating these components then, so if x is equal to r cosine theta, then x is going to be equal to r, which is rho sine phi, times the cosine theta. If y is equal to r sine theta, in terms of these spherical coordinates, r rho sine phi sine theta. Right, so now we can have a way of rewriting this x and y in terms of rho theta phi, okay? Y in terms of rho theta phi. And then lastly, before I forget, right, this dimension here, that space, this was our z before, right? So in that case, what is z going to be equal to? That's going to be the cosine, right? And we put it up here. You have cosine phi adjacent z over hypotenuse rho. That means z is equal to rho cosine phi, or cosine phi. So now we have these conversions for x, y, and z in terms of rho, theta, phi, and z, rho, and phi only. Okay. So when we start to look at that integral, integrating some function of x, y, z throughout this region E, its volume, we can identify in that region E that this can become a function of rho, theta, phi with these conversions. And now the big deal, the big discussion, what does dV look like? Okay. So looking at that coordinate system, now we're going to build up in that space again, this kind of spherical, if you will, little block of volume. Okay. So let's take a look at that. Okay. So if we have this kind of, again, circular spherical region that we're integrating, now what we're building is that in that space, right, we're going to kind of think about for our block how far rho we are out, how far down in phi, how far over we are theta to get to this little block of volume. And we're going to imagine stacking those little curved pieces throughout to fill that space. Okay, so that dV component arcing this way, as we saw before. Okay, like so. Again, I know it's a little bit cumbersome here. There's a good diagram on page 1087, probably a much better diagram of this block. Okay, and so let me put that note here. Page 1087 has a good diagram, a good figure to follow. Okay. And so when we look at that component, what you can see is that here, this should actually be kind of more arced. Because again, it's living inside that sphere. All right. And so we start to piece together then is a foam that this kind of width component, let me connect this out, sorry. There we go, hopefully a little bit better. But this little width, that's going to be a D rho, how far out we're going. Similarly, we had that kind of arc before with our cylindrical polar form before. This little inner part, right, that's kind of like our r d theta, but we didn't have r. Remember what r was? R was rho sine phi d theta. But now there's also some arc here, right? How far we're changing in that phi direction. Okay, how far from the top to the bottom? Because there's some arc to it, this is when you get a rho d phi. Just like we had r d theta. Now the radius we're talking about out is how far from the origin we're going, that inner, okay, part of it. Since we have a very small d phi, but the inner of the outer is not going to make a big difference, so it's this generic rho. But now to get from the top to bottom, how far might that angle changing? That's that d phi. So in turn, that dv becomes rho sine phi d theta d rho rho d phi, right? Those three components, phi, rho, phi, or probably theta, rho, phi. There we go, better. Bringing these two factors together, since it's all multiplied together, what we're going to see is we're going to get a rho squared sine phi, and then that d rho, d theta, d phi, we can organize however we wish. So now not only do we have like this kind of r d theta component, now for spherical, we have this rho squared, right? Don't forget that exponent, sine phi, with our different components, right? Kind of interesting there. So in the end, when we start to see these kind of functions that we're integrating to this three-dimensional space, and that region E is spherical, conical, right? A cone. Well, we can start to rewrite this as still dealing with that region E, but now having our function in terms of rho, theta, phi, and that dv component, rho squared sine phi d rho d theta d phi. Again, a lot to kind of convert if we have some complex function here. Most often as we start, it's going to keep it really simple so those conversions won't take too long. The real focus is going to be making sure we remember to bring in this factor with our dv, and then identifying those limits of integration we need for our region, okay? And I'll write up some examples, at least one example, two examples, hopefully, and hopefully the slides that I put up from the textbook can give some good examples there of some of these spherical coordinate systems being used to evaluate integrals. But I'll leave it at that introduction, get our mind wrapped around that, and then I can write up some examples to look at to help flow through this information. All right. Any questions, definitely let me know. Otherwise, I'll put this up and finish up this chapter. All right.